Hello and welcome to this first video tutorial for Mechanics of Fluids 1. Today we're going to look at the hydrostatics problem sheet from Brightspace, and we're going to look at how we solve question 1, which should hopefully help you solve the other questions by yourself. Looking at question 1, straight away the first thing that grabs us is that the geometry appears to be inverted. It's not like what we've seen in the lectures, but don't worry, this will, as you will see, can be solved in much the same way as the previous questions. So just to read the question, we have a closed cylindrical tank filled with water. It has a hemispherical dome and is connected to an inverted piping system as shown in the figure. The liquid in the top part, our grey liquid here, is of our piping system has a specific gravity of 0.8, so Sg here is 0.8, which means it has 0.8 the density of water. That is the definition of specific gravity. And the remaining parts of the system are filled with water. So the blue liquid here has an Sg of 1, Sg of 1. We're told that the pressure here in our gauge attached to the tank is reading a value of 60 kilopascals. So we're asked to determine then what then is the pressure here at PB of some pipe that we're measuring the static pressure of. And then we're asked to figure out what is the pressure head at the top of the dome at point C. So what is the pressure head at this additional height here above it? And we can get it in kilopascals. We can ignore the millimeters of mercury for now. So we could go and solve this problem by taking the balance of all the forces. So we know that the pressure here along this line here is 60 kilopascals all the way across the tank. So we could work our way down here, get the pressure at the bottom, get the pressure due to this column of water, due to this column of fluid, due to this column of fluid, and all the way down to get PB. But we don't want to do that because it'll take too long. And we know if we think back to the lectures, what I said was the way to solve this problem easily is to find the regions of equal pressure. And straight away we can draw the first one. We can say that across this distance here, this red line, the weight of the grey fluid acting here is equal to the weight of the grey fluid acting there. They're in equilibrium. It's a balance. Okay. Well, if that's balanced, then the other sides are balanced as well. So this side must be balanced with this side, which must be balanced with this side. Okay. So this means we can draw a line the whole way across the system, like so, which means that the pressure here at A, we call it 0.1, the pressure here at 0.2, and the pressure here at 0.3 are all the same. So this here is PA, right here, right across this point, this line here. And what's interesting about that is then, in order to get PB down here, we only need to worry about the fluid in this region here. We don't care about the rest of it. We can just ignore everything else. So we can say that PA, our pressure at point A, are 60 kilopascals, plus, because we're going down here, we're going down the first step, it's going to be our gauge fluid, so it's going to be gamma times, we'll call it gamma L for our first fluid, times 3 meters. If you forget what gamma is just rho times G. It's called the specific weight of a fluid, times 3 meters. And we're going to go even further down again, plus gamma of water times 2 meters. And that should be equal to the higher pressure at PB. And that's all we need to do. We've ignored the tank, we've ignored the left side of our piping system by simply recognizing with this red line across here, that the pressure must be balanced if the system is in equilibrium. That's very powerful. And then you can solve this. You know that PA, we're told, is 60 by 10 to the 3 kilopascals. We know that gamma L, our liquid, is rho G. We know that the fluid has a density of 0.8 times that of water, so it's going to be 0.8 times water is a density of 1,000 kgs per meters cubed, so that's rho of the gamma L, and then times 9.81, which is G, plus gamma W is just 1,000 times 9.81 times 2 meters is equal to PB, which is our only unknown, which means you end up, if you work that out, that works out about, I think it's 103 kilopascals. Simple. Now, we need to solve part B, which is figure out what is the pressure here at point C. What is PC? So the dome, the hemispherical dome here is probably going to catch you out, and the important thing to know is that the shape of the dome doesn't really matter. All that matters here is this vertical height. It's the weight of fluid acting here that determines the pressure, and we know that the pressure here along this red line is 60 kilopascals, so the weight of fluid upwards means we'll get a lower pressure. So we can say that PC is equal to PA minus, because we're moving up, remember now we're moving upwards, minus gamma times water times 3 meters. Okay, so PC is equal to 60 by 10 to the 3 minus 1,000 times 9.81 times 3 meters. And when you work that out, you get 30.6 kilopascals, which makes sense. The pressure at point C should be lower than the pressure at point A. So this is part B, this is part A, and you'll find this PDF on Brightspace.